Welcome to the Deep Dive, where we deliver comprehensive technical insights from the sources you trust, tailored precisely for you. Today, we're undertaking a highly focused technical exploration of learned image compression, or LIC. Specifically, we're dissecting what has long been considered, well, maybe the Achilles heel of high-performance codecs, the computational overhead introduced by the Gaussian mixture model, or GMM. We know GMMs deliver the best rate distortion performance, but historically, they've just been too slow for practical adoption.
That's absolutely right. For those of you deeply involved in optimizing entropy coding pipelines, you definitely understand this tension. GMMs are, well, essential really because they provide the necessary flexibility to accurately model the complex, highly non-Gaussian distributions of latent variables in modern compression networks. Yet until now, implementing them meant accepting a severe computational cost. It restricted GMMs primarily to research settings.
So, our mission today is to unpack a novel algorithmic solution that fundamentally changes this equation. We are diving into the specifics of FlashGMM, a new framework designed to eliminate this GMM performance bottleneck entirely. We're going beyond the headlines here to understand the architectural decisions and the numerical engineering that actually delivered these results.
Indeed, we'll detail exactly how FlashGMM re-architects the core entropy coding phase. The main technical insight we'll cover is the algorithm's complete circumvention of the legacy requirement for a pre-computed, quantized, cumulative distribution function, or CDF lookup table. This single architectural shift is responsible for the staggering speedups reported up to 90 times faster than conventional implementations. And crucially, all while preserving and perhaps even slightly improving that vital RD performance.
Okay, let's unpack the context of this problem then, starting with the fundamentals of the LIC pipeline for our expert audience. The core flow, it involves transforming the input image $6 into a compact latent representation, Aurora. This latent dollars is then quantized to Hede. The subsequent step, and this is the focus of our discussion today, requires modeling the probability distribution P-Mendello. This is the probability mass function that dictates the compression rate during entropy coding.
And the accuracy of that probability model is paramount. It really is. The better Peta fits the true distribution of Hede, the closer the resulting compression rate gets to the theoretical entropy limit. And this is where that historical trade-off between modeling power and computational viability becomes really stark.
Yeah, many state-of-the-art works, recognizing the computational trap of the GMM, have consciously settled for the Gaussian single model, or GSM. Can you detail the limitation of the GSM? Why is its simplicity both its greatest strength and, well, its weakness?
Certainly. The GSM is simple. It assumes a basic single normal distribution for each latent variable Garus. In our notation, that's matchcal Maya theta, E moi sigma. This assumption is computationally lean because we're dealing with well-understood mathematics and only two parameters per symbol, the mean mut and the standard deviation sigma nid. However, if the learned latent space is complex, which it usually is, exhibiting features like skewness or heavy tails, well, a single Gaussian just cannot accurately capture the full shape of the distribution. That inherently caps the maximum achievable RD performance.
Which brings us straight to the GMM, the necessary modeling extension.
Precisely. GMMs embrace that complexity. They have to. Instead of one Gaussian, the GMM models the distribution py theta as a weighted sum or mixture of different Gaussians. This is equation 2 in the source material, if you're following along. These weights, 24, they sum to 1, and the model essentially learns how to blend simple distributions to fit a highly complex empirical distribution. This flexibility is proven to yield significant gains in RD performance, often shaving percentages off the BD rate relative to GSM.
Okay, so the problem isn't the model itself, but the mechanism used to translate that model into a compressed bit stream. We have to discuss RANS asymmetric numeral systems, which are kind of the workhorse for entropy coding in modern LIC. They're chosen for their superior throughput and compression ratio. But why does RANS in particular introduce this GMM complexity?
Right, NS, while fast, operates strictly on quantized integer values derived from the CDF. It's fundamental to how it works. It requires knowledge of two things for every symbol being processed. Okay. The cumulative probability PCS, which is the sum of probabilities up to the symbol 1 to 1, and the probability of the symbol itself, ASTIOS. Crucially, when the decoder runs, it receives a normalized numerical state, let's call it $, and it must determine which symbol corresponds to that state. This is the inverse CDF problem, finding Hass PDF1D.
And this is where the analytical intractability of the Gaussian inverse CDF becomes the real bottleneck.
It is the mathematical roadblock, absolutely. The Gaussian CDF, it's defined via the error function, take text adrict x, which is itself a non-elementary function. It requires numerical integration. Consequently, its inverse, vi1xx, cannot be written in terms of standard elementary functions. There's no simple formula. Attempting to approximate CDF1 numerically, say, using iterative methods like Newton's method, it's just too slow for real-time compression. And it's highly sensitive to floating point precision near the symbol boundaries, which can cause, well, catastrophic decode errors.
So the traditional solution, adopted by pretty much every major framework, including Compress AI and the prior state-of-the-art optimized GMMs, was to pivot from analytical computation to basically data structure lookup, the pre-computed quantized CDF table.
Exactly. The lookup table avoids the runtime numerical solution for CDF1 values. You compute the CDF for every possible symbol in the alphabet dollars beforehand, quantize these probabilities to the precision required by ANS, like 216 or 2 $, and then store them. Decoding then becomes a simple matter of searching this table $2 for the stored quantized value closest to the decoded state dollars.
Now, let's zoom in on this fascinating divergence between GSM and GMM in this context. If the table is the solution, why does the GSM manage to avoid this computational death trap while GMMs just sink?
This is a critical point. It really exposes the architectural vulnerability GMMs faced. The GSM cleverly utilizes parameter constraints to minimize the dimensionality of the problem. It's quite smart, actually. When encoding a symbol distributed as Mathkill-Sum, they typically shift the problem to modeling Ezen's Mathkill deal. This removes a variable that affects the shape of the distribution. The only remaining shape parameters.
And what do they do with the sigma?
To manage complexity, the GSM approach quantizes sigma dollar into a small fixed number of levels, typically 64 logarithmically spaced values. Since the mean is zeroed out and sigma only takes one of 64 fixed constants, only 64 unique CDF tables ever need to be pre-built. These can be calculated once during network training or even just hard-coded. During inference, you simply look up which of the 64 tables corresponds to the estimated sigma, and the runtime penalty is negligible. It's very efficient.
That 64-level quantization is a brilliant piece of engineering, definitely. But it is fundamentally an approximation that restricts the model's flexibility. Does the literature on GSM discuss the inherent RD trade-off made by the community when they accepted only 64 variance tables? Does the GMM, even with FlashGMM speed, still retain an RD advantage primarily because it avoids the 64-level quantization constraint?
It does. Yes, absolutely. The 64-level constraint, while computationally expedient, introduces a modeling ceiling. There's no way around that. You're essentially forcing the latent distribution to conform to one of only 64 predefined shapes. The GMM, in contrast, has to estimate parameter by parameter, the means, standard deviations, and weights for all Gaussian components. And it does this for every single latent symbol, the $. Since these parameters are dynamic and determined by the hyperprior network for every symbol, you have, theoretically, an infinite number of resulting distribution shapes.
Meaning the GSM's optimization trick is just utterly useless for the GMM?
Completely useless, yes. Because the underlying distribution shape changes dynamically for every symbol, the CDF table must be computed on the fly. For every latent symbol during both encoding and decoding. If we review the complexity analysis of existing GMM implementations, the scale of this problem becomes clear. It's huge. The cost lies in constructing the full table, where Hattie is the number of latent symbols and dollars is the size of the alphabet, the range of possible quantized integer values.
And the theoretical complexity for constructing that table is, well, daunting.
It requires calculating TI-track $5 for all on-day interim. This involves summing up TI-track weighted CDF difference terms, as detailed in equations 4, 5, and 6 in the paper. This leads to a theoretical complexity of OKI, and that dependence on the alphabet size, the attrap, that is the computational killer. That's the term that hurts. If the alphabet size is in the thousands, which is common, you're performing millions of unnecessary floating point operations per image just to build a table you'll only search once per symbol.
Wow. And even GPU acceleration, which existing works like Compress AI and Lin et al. Used, couldn't bypass this fundamental cost, right? They were only speeding up the calculation of those OCO terms in parallel, not eliminating the dollar factor itself.
Exactly. They achieved impressive speedups, don't get me wrong, by parallelizing the calculation across thousands of cores. But the algorithmic complexity remained tied to the alphabet size. It was baked in. FlashGMM's innovation lies in challenging the necessity of that table construction entirely. It asks, do we really need this table? It's a fundamental architectural break from the reliance on a pre-calculated data structure.
Okay, so here is where the conceptual elegance of FlashGMM really shines. Instead of optimizing the computation of, all those OCO terms, the authors simply eliminated the table and solved the inverse CDF problem through a completely different mechanism. What's the fundamental mathematical property they leveraged?
The secret weapon is monotonicity. It's that simple, really. The cumulative distribution function, CDF dollars for any well-behaved probability distribution, and certainly for a GMM composed of Gaussian components, is strictly monotonic. As the symbol value $6 increases, the CDF value CDF tenfold never decreases. This property turns the CDF1D problem from an intractable analytical solution into an efficient search problem.
Okay, let's trace the flow of the new architecture then, starting with the encoder, which is comparatively simple in this new paradigm.
Yeah, the encoder becomes much simpler. In the FlashGMM encoder, when the quantized latent symbol he is received, the system just directly computes the GMM's cumulative probability, CDSTY. This calculation is a straightforward sum of granted-adolescent standard Gaussian CDFs. The computational cost for the encoder is minimal. It's proportional only to the number of latent symbols and the fixed number of Gaussian components dollars. Since small, usually 3, this is extremely fast.
Right, the complexity bottleneck always resided in the decoder's need to solve CDF1.
Yeah.
So how does the decoder use that monotonic property to perform the dynamic binary search without the table?
Okay, so the decoder treats the GMM CDF function, CDFY, as an oracle that it can query dynamically. Think of it like that. When the decoder receives the normalized state dollars, it needs to find the integer symbol that satisfies the condition. Because the CDF is monotonic, we can perform a standard binary search over the entire alphabet dollars to find this target symbol.
Ah, okay. So instead of a simple lookup in a pre-made table, the decoder is performing successive calculated guesses. It's having the search space with each attempt until it locates the correct probability bin corresponding to that state dollars.
Precisely, yeah. For a concrete example, let's say the alphabet dollar spans from, $2,000 to plus $2,000. The decoder initially tests the midpoint, maybe $90. It computes the CDF at $9. If CDS dollars is greater than $1, the target symbol must be in the negative half, right? If CDF dollars is less than $1, the target must be in the positive half. This process repeats dynamically, chopping the search space in half each time. The complexity of each search is proportional to log $1.
Wait, let's just zoom in on the magnitude of that complexity reduction again, because that is the entire basis of this breakthrough. The complexity is drastically reduced from OKOAY. That's huge.
This transition is the single most important mathematical result of FlashGM. It really is.
Yeah.
Let's quantify it for our expert audience because the numbers are striking. In modern high-rate compression, the quantized latent alphabet size, $2 often needs to be substantial to maintain precision. It can easily exceed 214 or 215, maybe up to 16,384 or 32,768 possible values.
Okay, so if the alphabet size dollars is, say, 32,768, you are comparing 32,768 operations in the old way
To log 2, $32,768, which is exactly 15 operations. 15. In practical terms, the algorithm replaces a multiplication factor of over 32,000 with the multiplication factor of about 15. This isn't just a marginal speedup. It represents an asymptotic architectural change. It eliminates the computational dependency on the alphabet size. The complexity cost becomes virtually independent of how wide your alphabet needs to be, which is just crucial for high-fidelity compression.
Furthermore, the paper highlights a key assurance regarding numerical stability. Since we avoided the traditional unstable numerical inverse CDF solution, and we're also avoiding the quantization errors introduced by the pre-computed table, what's the core guarantee of accuracy here?
The guarantee is absolute encode-code synchronization. That's the key. Since both the encoder and the decoder are using the exact same numerical function CDF, they're just operating in forward and inverse modes, respectively, they will always agree on the result. Provided, of course, they are using the same floating point precision libraries. We're not solving for CDF1 using potentially error-prone numerical approximations. We're leveraging the inverse mapping property inherent in the binary search on a strictly monotonic function. This is a critical distinction. It ensures the bit stream is perfectly reconstructible, a requirement that absolutely cannot be compromised in compression.
Okay, so the dynamic binary search eliminates the table, solves the architectural bottleneck, and delivers that dolly-wall complexity. Fantastic. But the speed of the algorithm is now directly dependent on how quickly we can execute that GMM CDF function CDF within the loop, right? As we discussed, the standard Gaussian CDF requires costly numerical integration.
That's the next level of optimization the authors pursued. accelerating the actual function calls.
Exactly.
They recognize that while mathematical precision is important, if a computationally cheaper closed-form approximation of FISTA is good enough for the RNS quantization levels, it could significantly boost performance. So they benchmarked 3 different closed-form approximations.
Let's review those candidates in detail. It's a fascinating comparison of numerical trade-offs, I think.
Okay, first they tested the Polya approximation, equation 8. This is a very elegant, simple formulation. FISTA is 1 plus class quarter 1. While it's easy to compute, its accuracy often falls short for high-precision applications. It's maybe too simple. Second, they examined the Abramowitz and Stigen, or ANS, approximation, equation 9. This is often considered the gold standard for many scientific computing tasks. It involves the standard Gaussian PDF ZX combined with a ratio of polynomials and specific fixed constants in feces. It's much more complex algebraically, but it provides vastly superior accuracy.
And the third candidate is highly recognizable to anyone in the deep learning community, mainly due to its connection to activation functions.
Indeed, the logistic function approximation, equation 10. This approximation, often used in the context of the Gaussian error linear unit, GLU activation function, is computationally lean. Verplast is off till 2, x equals 1.702 x plus 2 naught. It basically substitutes the complex error function calculation with simple exponential and division operations. Much faster.
Right, and the ablation study results in Table 2 are where we see the critical trade-off between mathematical precision and practical performance. For the ANS approximation, the authors report an incredibly low maximum error, less than $7, 5 times 10, $8. Why would we ever risk moving away from that level of robustness? Seems counterintuitive.
Well, the ANS approximation is essentially mathematically equivalent to the C++ standard library baseline using std.efc. They're very close. Both achieved an identical BD rate of medical 4.24% relative to the GSM anchor. So, from an RD perspective, it's solid. The reason to deviate lies entirely in the pursuit of marginal speed and, surprisingly, potential modeling benefits.
Okay, let's talk about the surprise winner then. The logistic approximation. It's the least mathematically precise, yet it delivered the best overall compression results, achieving a BD rate of medical 4.28%. How does that happen?
This is definitely the most counterintuitive result in the paper.
Yeah.
The logistic function, despite being a deliberate simplification, somehow provided a better fit to the actual learned probability distribution than the mathematically perfect GMM calculation did. The author's hypothesis here is quite powerful. The training process, specifically the hyper-prior network learning the GMM parameters, doesn't result in a perfect canonical Gaussian mixture. It just doesn't. The latent distribution is inherently imperfectly modeled, and the simplified, closed-form structure of the logistic function approximation coincidentally provides a better match to this imperfectly learned distribution. That leads to a fractional gain in rate distortion performance. It's a fascinating outcome.
So the recommendation in the paper seems clear. Use the logistic approximation for optimal RD performance, leveraging the sort of serendipitous fit. But default to the ANS approximation if absolute highest mathematical robustness and guaranteed minimal error are the primary concerns.
That summarizes the ablation findings perfectly. Yes. However, even with the $Wika complexity reduction and the acceleration of the Fangzheng calculation via approximation, we still face the overhead introduced by those Dalager components. For every symbol, we still have to sum tele-weighted CDF terms. That cost hasn't disappeared entirely.
Right, and this is where SUMD single instruction, multiple data parallelization, becomes necessary to neutralize that remaining factor of tolerance.
Exactly. Since the calculations for the Gaussian components are mutually independent, they are perfectly suited for vectorization. It's an ideal use case. By leveraging advanced SUMD extensions, specifically AVX2 in this case, the processor can execute the same arithmetic instruction concurrently on multiple data points.
And since typical LICGM models have been empirically shown to perform optimally with a relatively small number of components, like K33 around or maybe 41 hour.
That small dollars is highly advantageous here. AVX2, for instance, operates on 256-bit registers. This allows simultaneous processing of 4 single-precision floating-point numbers. Since K33 fits comfortably within the AVX2 capacity of K42R components, the entire process of calculating the weighted sum of DDFs can be executed in a highly vectorized manner. The computational overhead introduced by dollars in the complexity factor, nor K log y, is thus effectively minimized by hardware parallelization. It renders the overall computational burden relative to GSM pretty much negligible. This combination of architectural redesign and vectorization becoming effectively all in practice is the true source of FlashGMM's efficiency.
Okay, theory and optimization are impressive, but the proof is always in the results, right? The authors used the well-established checkerboard model architecture and tested it against the standard Kodak dataset. We need to focus on two key metrics: the BD rate comparison anchored to the GSM result and the raw execution time across different hardware environments.
Let's start with the total runtime comparison presented in Table I in Figure 1. We really have to recognize the huge gap between the baseline Compress AI GMM and subsequent optimizations first. The test environment mentioned was a pretty standard configuration: an i7-7700 CPU and an RTX 2080 Super GPU.
Let's break down the end-to-end compression time. This includes the transform, the hyperprior network, and the entropy coding step itself.
Right. The conventional GMM implementation in Compress AI, that's the widely used PyTorch library, took a staggering 20 milliseconds for total compression, over 2 seconds.
Wow.
The optimization work by Lin et al. In 2023, which used high-speed PyTorch C++ extensions to parallelize the table calculation on the GPU, significantly reduced this to 271 milliseconds. And this was previously considered state-of-the-art for FastGMM. Pretty good, but still a quarter of a second.
Okay, now compare that to FlashGM's result in the same environment.
FlashGMM delivered a total compression time of just 56 milliseconds. 56. When you compare 20 milliseconds to 56 milliseconds, FlashGMM is approximately 36 times faster than the conventional implementation end-to-end, and is closer to 90 times faster if we isolate just the encoding step itself, which we'll touch on.
Let's be critical for a moment, though. The Lin et al. Optimized version already cut performance down by nearly a factor of 10, which is impressive. FlashGM still beats that highly optimized GPU baseline by almost a factor of 5, 4.8x. Where specifically did the Lin et al. Optimization fall short that FlashGMM overcame? What was the key difference?
Well, the Lin et al. Method, despite being fast, was still fundamentally constrained by that OI complexity. It couldn't escape it. They used the GPU to calculate all the table terms Tij very fast, yes, but they still had to calculate over 32,000 values for every symbol. And then they had to transfer that data for use in RANOS. FlashGMM just eliminated the entire 32,000 calculation step altogether. It replaced it with a mere 15 binary search steps performed dynamically on the CPU, actually. The difference is architectural, not just about parallelization efficiency. It's a different way of thinking about the problem.
And the isolation of the entropy coding time specifically is the ultimate proof that the bottleneck was truly eliminated.
Absolutely. That's where you see the raw impact. The Compress AI GMM encoding time alone consumed 1965 milliseconds of that 2020 total, almost all of it. FlashGMM encoding time dropped to an astonishing 22 milliseconds. 22. This confirms the complete success of eliminating that costly dollar cable construction factor. The coding is now so fast it's no longer the dominating computational step in the pipeline.
What's also highly compelling, I think, is the comparison to the GSM anchor itself. In that normal environment, the optimized GSM implementation took 65 milliseconds for total compression. FlashGMM, running the more flexible GMM model, took only 56 milliseconds. It's faster than GSM.
This is a profound point. Yeah, it's really significant. FlashGMM isn't just a fast GMM. It's faster than the currently established, highly tuned, production-ready GSM implementations. This strongly suggests the architectural simplicity achieved by replacing table lookup with dynamic binary search, combined with efficient CDF approximation, creates an algorithm that is computationally superior, even compared to the historical speed champion, the GSM. The authors rightly note this points to optimization headroom even in current GSM algorithms. Perhaps they could benefit from similar dynamic search techniques too.
Okay, moving to the rate distortion performance. Figure 2 shows the RD curves, and the BD rate results are crucial here. We might have expected FlashGM to just match conventional GMM, but it actually performed marginally better. Why did the method of inference result in a better compression rate? That seems odd initially.
Right, the underlying model training remained identical, so the improvement can't be from the model itself. It must be in the fidelity of the probability assignment during inference. The conventional GMM methods, relying on table construction, introduced two main sources of error. First, there's the necessary quantization of the CDF values for the RNS table. That loses precision. Second, the search process itself involves finding the closest quantized entry, which might not be perfectly accurate.
And FlashGMM bypasses both of those potential error sources.
Correct. By utilizing a pure shared numerical function and dynamic binary search, FlashGMM adheres more faithfully to the probability distribution learned by the hyperprior network.
Right.
There's less approximation involved at inference time. The authors attribute the slight RD enhancement from the conventional GMM's -4.02% BD rate to FlashGM's -4.28% to the omission of this noisy distribution modeling during inference. Essentially, the model's confidence in its learned parameters is better preserved when using the cleaner table-free method.
And it's particularly notable that the logistic approximation delivered the best result, negative 4.28%, while the highly accurate ANS approximation was slightly worse, negative 4.24%. This really reinforces the idea that the slight RD gain is tied less to pure mathematical precision and more to the practical, clean adherence to the learned latent shape, even if that learned shape is itself imperfectly Gaussian.
Exactly. It's about matching what the model actually learned, warts and all, rather than forcing it through a perfectly precise but potentially mismatched mathematical function during inference.
So synthesizing this deep dive, the significance of FlashGMM is clear. It really has resolved this decade-long computational bottleneck that plagued high-performance GMM-based learned image compression. The core breakthrough was the elimination of the fixed lookup table, replacing that intractable OK complexity with the logarithmic-dependent and far more efficient dynamic binary search operating in old-quell Y time.
And this architectural redesign was supported by necessary technical finesse, the strategic adoption of the highly efficient logistic CDF approximation, recognizing its practical superiority over purely precise approximations in this context. And of course, the leveraging of SIMD vectorization to fully mitigate the remaining computational factor of taxolar components. This isn't just theoretical optimization. This makes GMMs deployable in practice.
The implication for the field of compression is profound. GMM-based codecs, previously restricted due to runtime cost, are now practically viable for broader adoption in real-world high-performance applications. It opens up possibilities.
This work directly frees up expensive computational resources. That's a big deal. We're talking about GPU cycles previously dedicated solely to calculating and transferring large CDF tables that can now be used elsewhere in the pipeline. Or they can simply contribute to faster overall throughput in commercial implementations. The era of having to sacrifice RD performance for speed, at least for these latent variable models, seems definitively over.
Okay, so FlashGMM demonstrated superior BD rate using the logistic approximation, a closed-form simplification rooted in the GLU function compared to the mathematically rigorous ANS approximation. This outcome challenges a long-standing assumption in compression research, perhaps. It raises an intriguing question for you, our listener, to think about for future entropy modeling. Since the true learned latent distribution is imperfect anyway, could the compression community benefit from intentionally training models against non-Gaussian closed-form probability distributions? One's known a priori to be computationally cheaper to calculate and invert. Could we explicitly leverage this coincidental fit phenomenon rather than always aiming for mathematical perfection with Gaussian mixtures? It suggests performance gains might lie in models tailored not just for distribution accuracy, but maybe more for computational codability, something to ponder.